Hello, I welcome you back to another episode of the Plant Growth and Development series. Here we've already been talking about growth in plants. We've seen what is growth and how we can measure growth. Today we're going to start talking about growth rate. Growth rate word is in general used for anything when we observe a parameter in relation to time. So when we talk about growth rate, we are trying to study growth per unit time. So, what exactly is growth? It could be an increase in the length, it could be an increase in the width of the plant, it could be an increase in the cell number. Whatever the parameter is, that increase per unit time is the growth rate. Let's say a leaf increases by 5 centimeters square in area. So, we'll say it increased in 5 centimeters square in 1 day. So, in relation to time, it becomes growth rate. Now there are two models to study growth rate. One is arithmetic model and second is the geometric model. Both of the models are applicable and seen at different places in the plant body. Let's understand each of them one by one. So let's begin first with the arithmetic growth rate. Well, the arithmetic growth rate is the gradual model. In arithmetic growth, we observe that one cell undergoes a mitotic division to form two daughter cells. Yes, that's natural. So one cell went a mitotic division, it undergoes mitosis and forms two daughter cells. Now, out of the two daughter cells formed, only one daughter cell will continue to divide. What is going to happen with the other daughter cell? Well, the other daughter cell undergoes a process known as differentiation. So what is differentiation? As we have discussed earlier, I'll just recap that for you. Differentiation is the process where any cell loses its ability to divide and takes up a specialized function. A meristematic cell might get converted into a xylem cell. It might get converted into a phloem cell. So this process is known as differentiation. So one of the cells got differentiated and the other one continues to divide. So now this cell is going to divide and form two new daughter cells again. Well, wonderful. And we had this cell that had already differentiated. Again, this process is going to get repeated. This cell will continue to divide and this one is again going to get differentiated. So what we observe is that in each step, only one new dividing cell is formed. This, therefore, is a very gradual process. So this is a cell by cell increase in a gradual fashion. Now, if we had to depict this situation graphically, we expect the graph to be linear. Why? Because cells are getting added step by step in a slow fashion. So let's plot a graph and see what we obtain. So if we plot a graph, let's take length, increase in length of the stem as a parameter for growth. So here I'm going to write increase in length and I'm going to observe it over a time period. As I've already discussed, we obtain a linear graph. Why? Because cell by cell an increase is observed. An equation to describe the situation is LT is equal to L naught plus RT. So this is the equation to describe arithmetic growth. Let's discuss what each of the terms mean. Well, LT refers to the length of the plant at time t. L naught is the length of the plant initially at time equal to 0. So this represents the initial situation. R refers to the growth rate, which in this case is going to be increase in length per unit time, and T refers to the time duration. Let's say here this time duration during which I have done the study. In geometric growth, the increase in cell number is not gradual. It's a very fast increase. Why? Here let's say I had one cell. Now this cell would again go a mitotic division and form two new cells, as we have seen earlier. Now in this case, none of the cells is differentiated. Both of them continue to divide. So now this cell is going to add two new daughter cells, and this cell is also going to add two new daughter cells. So instead of one cell getting added each time, the increase is something like this. One cell to 2, then to 4, then each of them will produce two new daughter cells, 8, 16. So it's a very rapid, it's an exponential increase. This is basically an ideal case scenario. This is observed only in certain situations in plants that we're going to observe in the next one. Now let's move on and try to depict this situation graphically. On plotting a graph, a S-shaped curve is obtained. An S-shaped curve is obtained, having three phases. The first phase is known as a lag phase. The second phase is known as an exponential phase, also known as the log phase. And the third phase is a steady situation. So this, again, as I've already discussed, is a curve of whatever parameter you're considering. Let's say it's growth rate that I'm considering over time. So what do these three phases represent? Let's talk about that. Lag phase, as we see, is a very slow increase in the cell number. Why does this happen? Because cells, to undergo a very rapid division, need to accumulate nutrients. They need to prepare themselves. So lag phase basically represents that preparation time. Exponential or log phase is the phase of very rapid cell multiplication. So here what we are observing is basically the exponential phase. After that, what happens is the exponential growth starts to decrease and we start to approach a steady state. Why is that? Well, we are observing in exponential growth that the nutrients are unlimited. There is no competition. The nutrients are going to be there forever. Oxygen is not limiting, sunlight is not limiting, water is not limiting. Is that true? Well, it's not true. No resource on this planet is unlimited. So as the resources begin to deplete, some resources are going to become the limiting factor. Due to the limiting factor, growth is going to slow down and settle into a steady phase. So this curve, the S-shaped curve obtained, is known as the sigmoid growth curve. It is known as the sigmoid curve. So now an equation to represent the situation would look something like this. Wt is equal to W naught e to the power RT. Again, let's discuss the terms. W, let's say in this case, is increase in the weight of the plant. It could be any other factor, length or whatever you're considering at time t. W naught again represents the initial weight, the initial scenario. E is the natural base of log. R refers to the growth rate. And T again is the time duration during which you're plotting your curve. So now let's move on and talk about where exactly these growths are observed in the plant body. The first cell of the plant body is the zygote. Right. So when the zygote is formed, it has to undergo a very rapid cell division. Why? So that it can form the plant body quickly, the seed can germinate. So after the zygote undergoes the division, initially to 2 cells, then 4, then 8 and 16, so on. This initial phase is very rapid and therefore represents your geometric growth. So this is the phase of geometric growth. Eventually, this geometric growth settles into a more realistic situation where different organs are growing. Let's say I have a leaf that has already formed. The growth in that leaf is going to be more realistic, more gradual. Eventually, it will get converted into what we know as the arithmetic growth rate. So both of them are actually observed in the plant body, but geometric growth is observed for a very short period of time. Arithmetic growth is the more realistic model and is seen throughout the life of the plant. Well, that was all for today. Thanks for watching the video. Don't forget to subscribe to the channel, and let's meet in the next video.